All right. Welcome our next speaker, Herman, and he's going to talk about Marvell's acceleration with OVS. So good luck.
Yeah. Hello, everyone. I'm Herman Kalra. I'm accompanied by Jaren Jacob. So he is joined us online, and we are from Marvell Semiconductors. So today's talk is about like how integration of Marvell CN10K DPU with OVS has resulted in significant boost in performance. So to get started, so just a quick overview on the hardware offloading feature, where like today world, every packet counts, every microsecond counts basically. How efficiently a packet has been handled makes the difference between smooth operation or a bottleneck. So OVS has kind of addressed this performance barriers and offered a control stack with which like we can offload some high latency tasks into the hardware and get the best performance, and while freeing up the resources, CPU resources, basically for other critical tasks. So the diagram on the right, basically, it talks about the packet movement in a SRIOV-enabled environment where, let's say, a peer or a remote machine wants to communicate with the VM. So exception path, the packets will be handled by the OVS. Basically, it takes the packet enters the card basically from the PF interface and gets routed to the VM via its representer. Basically, the representer is a virtual port for which is representing the VF and which manages and monitors the traffic through it. So, except as I said, like exception path will be forwarded, and once the OVS has classified the rule, has classified the packet, then basically all the subsequent packets can take the fast path, as in like it directly goes from the hardware switch to the VM. So there won't be any involvement. So OVS kind of gets bypassed. So some introduction to the Marvell Octane CN10K DPU. So Marvell CN10K DPU has many SKUs which can incorporate up from like 8 to 2460-bit ARM Neoverse and 2 cores, which can speed up to 2.7 gigahertz. And it can support up to 6 DDR5 DIMMs, which can operate at 5600 MTS. So one of the SKU has an integrated switch, while the other SKUs can leverage the OVS solution for getting the switching capabilities. CN10K offers comprehensive hardware accelerators, which include machine learning and artificial intelligence acceleration, a true inline protocol IPsec, which includes the inbound and outbound IPsec, highly programmable packet processors. So we'll be talking about each and every hardware block in like our subsequent slides. So it also offers a rich set of input outputs, such as support for PCIe Gen 5 plus the MaxX support with for 16 into 50 gig Ethernet lanes with MaxX support and up to 56 gig SerDes lanes. So let us now look at the packet walkthrough, like how when the packet enters the NIC card, like so initially, like it meets the NPC block, which is the network parser and the CAM unit. So where the packet gets parsed and the flow is basically identified. So let's say for this use case, it's a normal forwarding flow action. So then the packet basically reaches the NICs, which is the NIC controller unit, which does manages our input output of packet. So CN10K does has a network pool allocator for which for the buffers we can allocate for the packets we can allocate buffers for it. So it's the so during the RX configuration there are some crucial decisions which can be made, such as whether the packet has to be enqueued to a completion queue. Basically, this is our traditional descriptor ring where the pointers can be added, or it can be added as a WQ entry to and can be added as a work to the SSO, or the packet can undergo policing, so ingress policing, where some limit can be set for the ingress traffic, and some consequences can be action if consequent action, like if the limit has been crossed. So once it is decided, the ARM can basically pull off the packets from the CQ ring, or it can get work. And once the business logic process on that packet is being done, so the packet can basically be enqueued to the SQ. So here the packet can undergo a hierarchical scheduler, shaping, coloring. So to achieve the QoS, basically quality of service. So everything is kind of can be offloaded to the hardware. So it can be these SQs can be configured like per port. These can be configured. Plus there can be L3, L4, up to 2, meaning inner and output hardware checksum offload can be enabled. PTP timestamping can be enabled. So there are some configurations which can be done at this stage. And then the packet is passed on to the NPC where it can be, where the link for the next, like where the packet has to steer, whether it has to go to the PCI host or it has to go out on the wire, or it can be looped back into the hardware. So basically there, the decision has been made, and also the buffer can be freed back to the NPA. Also at this stage, at the NPC stage, basically some more offloadings can be configured, such as VLAN tagging or some multicast packet replication. So there can be more things can be done. So this was about the plain packet. So talking about, let's say we received an encrypted packet. So if the packet, once like it is recognized that it's a encrypted packet and the inline IPsec, let's say it's configured, the packet reaches the crypto accelerator unit where the packet gets decrypted. And once it gets decrypted, it can be looped back to the NPC unit, and it can follow the same plain packet what we just discussed. So here, like I would like to say, like it's a inline protocol IPsec, which means that there is no ARM core involvement for header formation or header removal. So it's totally done by the hardware. At the outbound IPsec case, the packet is handed over to the, so ARM cores can request for encryption of the packet once it goes out. So CPT block can do it for us. And once it's done, it goes back to the NIC controller unit, and then it can be steered outside. So ARM cores does have a direct, it can do the software buffers allocation directly from the NPA. And CN10K offers look-aside engines like for MLA, ML, ALI, DMA for timer. So ARM cores can basically NQ and DQ such packets and get the respective operation done. So transitioning the same diagram, like say what we saw for the hardware view. So if we transition the same diagram into the software view, like we can see that each and every block has a mapping to a DPDK framework. It has like the NPC block is capable of handling the RT flow operations. NIC's unit can be represented by RT3dev plus the RT meter for doing the ingress policing. Then the SSO event dev, RT event dev represents the SSO. And on the transmit side, RTTM basically. So RTTM, we can configure the traffic management basically entirely for achieving the QoS. And then all these look aside, like so the what we listed. So each and every block has a respective framework, DPDK framework, such as like ML has RT ML dev, so which is recently upstreamed. And then for crypto, like look aside crypto, if you don't want to do the inline IPsec, so look at this RT crypto dev can be leveraged. Plus, like there are some software libraries which the ARM cores can use anytime. So I mean, like I'll skip these slides. So this is for the future reading basically. So here we have mentioned about all the what all DPDK subsystem are mapped to, what all are abstracted in which hardware, and some more details on it. So for some future reading. So coming to the solution, like what we kind of designed. So here, as we saw in the first slide, like so exception path is handled by the OVS, and then like once OVS has recognized the flow, it offloads into the hardware, and then we saw that the packet passes through each and every hardware accelerator and kind of uses each whatever the hardware accelerators CN10K offers, so it's kind of using it efficiently. So it's an optimized path where the fast path is kind of offloaded, and then maximize hardware utilization, and which kind of frees up the CPUs for other critical tasks for running business unit. So this is an important point. I mean, like we kind of made sure that there should not be any custom changes to the OVS, so that like it gives us a seamless integration with the standard frameworks which can run over the Marvell platforms. So while designing the solution, we kind of hit some hardware constraints. So we have already communicated it to our hardware team, and we are working on that. So for that, like we implemented, we kind of mitigated them with some software implementations, and so just to enhance the overall functionality, so whatever we can offer. Right? And plus, this solution can be configured with the standard OVS utilities, just to simplify the network configuration and management. So now let us go through the packet flow in the how the solution look like. So this diagram is like from the first slide itself, like which showed us that the OVS holds the PF interface, while the VMs can hold the VF interfaces. Plus, they have a representer in the OVS bind to it. So in the first, like VM1 to VMN, so basically like for getting the packet from the host to the OVS, we needed some kind of a mechanism which can receive the packets from the host and can relay it to the OVS. So for which actually we implemented this OVS offload engine, which is a companion app which works in tandem with the OVS. And this engine will kind of make sure about the fast path basically. So OVS does the MAC learning and kind of broadcasts the ARP. So initial packets being the ARP request. So it will broadcast the ARP. For simplicity, I'm just not showing every traffic, but it will just to the port like for which the packet was kind of destined. So the packet was destined for VMN. So VMN replies to the ARP request, and then the OVS classifies the flow. It offloads it into the NPC hardware. And once the flow information has been added, so it kinds of take the fast path like it. So yeah, it's a hairpinning. So for this, so this was one of the hardware constraint we like kind of hit that. Okay, the hairpinning support kind of right now is done by the software. And then talking about the wire to the VMN. So let's say the initial packet comes from the wire. So from the PF interface, since it doesn't find any match entry into the hardware block, NPC block. So basically it goes to the PF, and from the respective representer, it goes to the VMN, VM1, and the hardware information OVS classifies, offloads the rule, and from next time the packet takes the fast path. I mean, and OVS won't be touched by that. Even and not just the packets which are the VFs which are part of the OVS engines can get the OVS benefit. There can be some VMs which are running on the Octeon itself, on the SmartNIC itself they are running. So they can have a representer in the OVS. The packet flow can be offloaded, and then it can directly take the fast path. So for the tunnel offloading, basically, let's say the VMN is configured that whatever the traffic goes out on the wire should be encapsulated. So initial packets goes to the OVS. So for initial packets, OVS does the encapsulation. It adds the, let's say example, VXLAN header and send it over the wire. The response packet, once it receives, OVS does the decapsulation and sends back the response to the VMN. And as well, it kinds of offloads the flow rules into, okay, what all action has to be done for identifying the packet. So here, this was another constraint we hit was that CN10K currently supports parsing of the NCAP packet. Like it can parse the packets, but the NCAP and DCAP action, we are kind of adding it in our next gen. So for that, like we implemented a NCAP DCAP unit, so which can kind of so in our further slides, like we'll show like so this how like we optimized this particular thing. And so once in the fast path, it can take the fast path. Basically, the packet, the NCAP unit can add a header, add a VXLAN header to it, and can get the packets out. And so, but we like for VLAN tagging, so all those actions are available. So this NCAP was missing, so that's kind of getting added. So feature scaling with the modular DAO. So I'll talk about DAO in a moment. So so this was transitioning, building up on from the last building up from the last slide, basically like we have OVS and OVS offload engine, where the exception path is kind of taken care by the OVS. And then once the packets has been classified, the flow rule is prepared. So how actually it happens is like the flow information is kind of communicated to the OVS offload engine, so that the flow management unit, which is part of the OVS offload engine, is connected to a flow library. So we have a flow library. This library kind of does the actual offloading it to the hardware, and it kind of manages the flows as well, meaning it takes care of the aging, meaning so there is a software and then there's a backend hardware. So whatever the flows are coming in, so he take care of it. And if non-active flows are there, so it kinds of ages them out. So once the flow information is there in the hardware, so it takes the fast path. Plus, like as I mentioned, that NCAP and DCAP unit is integrated with a packet transformation library. So this packet transformation library is kind of implemented, highly optimized implementation of adding, doing the packet header manipulation. Basically, it can add a NCAP header, or so there will be like, I'll be talking about the connection tracking basically. So manipulating the TTL, and also this library is capable of doing it. So flow library also supports the flow cascading. So where the output of one action can be like hierarchical flows, like from one flow to another flow, it can jump off. So this, which was a very important requirement for connection management. And for that, like we have implemented a connection tracking library, which takes care of connection state management plus the stateful protocol tracking. So this also kind of interfaces with the packet transformation library. So all these shown on the right side basically are the DAO components. I mean, like, which is a data accelerator offload. So it's a framework which Marvell has like recently proposed. So this, as part of the DAO framework, there are some components, applications, and libraries. Some solutions are there which can empower the CN10K Marvell CN10K DPU, and can help the users and the Marvell technology partners to get the breakthrough network performance. So this was about that. So certain challenges like we faced while working on it. So as I mentioned, so there were some protocols and actions which are not supported by the hardware. So we kind of implemented as a software component for all those unsupported, and they are part of the DAO flow library. Another thing is like the packets cannot be relayed directly to from the host to the MAC port. Basically, we needed some kind of a L2 forward mechanism. Like, so OVS engine did it for us. So the packets can be received from the host port and can be forwarded to the MAC ports. So same for the hairpinning also, this can be done. So yes, definitely a small fraction of ARM cores currently are being utilized for performing this software task as part of the solution. But yeah, we are kind of working to optimize this ARM core utilization and offloading everything into the hardware for the future platforms. Yeah, this was one of the issue which we faced with the OVS. I mean, so there are like some scenarios where in OVS non-PMD threads kind of attempts to transmit a packet. So our PMD, TX PMD, CN10K transmission routine is dependent on the RTL core ID basically. So basically the transmission region we identify just to avoid any if-else condition. So we kind of leverage this L core ID, and we determine the doorbell region where exactly the packet has to be sent. So that so for non-PMD threads, this was coming as invalid. So invalid base address was calculated and was causing the system crash. So we had to make some custom OVS change where a non-PMD thread, like when it's just attempting to do a packet transmission, can register for a valid L core ID. So there are some APIs like the attach and detach. So we can get the L core ID, and like once the transmission is done, so rolling back to the original state, like we're deregistering it from the L core ID. So currently, like as we saw in our previous talks as well, so currently no support for connection tracking for the DPDK providers. So we are kind of trying to enhance the OVS connection tracking for DPDK providers using the RT flow connection tracking capabilities. So we are kind of working on it. So with the OVS library plus some changes in OVS, we are trying to achieve the targets. So talking about the solution milestones, so till date, like we have the plain packet switching happening between the host VMs and as well as the outside network, plus the VLAN tagging traffic, enabling the tunnel offload with the optimized software. So these have been completed. So currently we are working on the connection tracking plus the advanced flow management where we can support the flow offloading and the cascaded flows. Plus, so this is something like which we would like to contribute to the community, where we can enable some or hardware offloads, such as like IPsec, like so, making use of the RT security in the data path. So currently, like OVS data path is kind of bypassed. So we can, if we can introduce some RT security flavor to it. So and plus the QoS, so a hardware offload version of it. So I think today we have the software implementation of for the QoS. If we can introduce the RTETEM traffic management, so that is another thing. And would like to propose a connection tracking offload for the DPDK provider. So whatever the solution we are coming up, so we'd like to contribute to the community. So to summarize, so the OVS hardware offload feature improves the performance significantly, synergizing. So today it's a synergy between a hardware and software components to achieve the overall functionality, plus some extra ARM cores available for business logic. So it's a reusable solution. So for our upcoming SoCs, so it's a seamless integration with the standard frameworks such as OpenShift OVN, and plus the feature scaling will be modular with the DAO libraries. Yeah. Thank you.
All right. Thank you. All right. Do we have any questions in the room?
I didn't get if you are using, we have native offload on the upstream, the doing in-cap. And
Sorry, can you please be a bit loud?
we have on the upstream, we have already in-cap and VLAN push and some other implementation on top of RTE flow. Did you connect it to that, or you had your own implementation?
So currently we have the same like RT flow, what the OVS, like whenever it classifies and it sends the RT flow rules, right? So we are using the same RT flow rules, and we are offloading it to the hardware.
So you are connected to the native offload provider. This is your connection to offload? Native,
Yes. Yeah, there is a connection between the OVS. So that flow rule is kind of communicated to the OVS engine, OVS offload engine. So it's a Unix socket between them, and that's how like we are communicating the RT flow definition to it, and we offload it from there. Plus, like from OVS also, like for the PF specific rules, the OVS PMD can directly do it for us. So we have that PMD support in the OVS, so it can kind of does it for us.
Okay.
Okay.
Hello, can you hear me?
Hi.
This is Martin from D Nation. Thank you for the nice presentation. Part of our activities is that we are Red Hat Advanced partners also for OpenShift specialization. So I was wondering, when you say about close integration of your solution with OpenShift, what exactly does that mean?
So by that, I mean like we should not have any custom changes to the OVS. That's first thing, like whatever the vanilla OVS has. So it should just work. So this OVS offload engine is what all we need extra. So once that is there, so once it's there, so we can have the complete. So data path will be taken by the OVS offload engine, while the configuration control path will be taken by the OVS. So the OpenShift and everything gets well integrated with that.
All right. So does it mean that when I take the OpenShift release and I install it on the bare metal and there is your hardware, it will somehow automatically work?
Should, I think, yeah.
Okay, thank you for explanation.
All right. Any more questions? Yep.
In terms of connection tracking, So OVS or OVN today uses some specific flags and all, right? Like how you are making sure like it's exactly replica of current contract module.
Yeah.
In the
So
kernel.
yeah, as we saw like in previous presentations also, so initially the connection is established by OVS only. So all the initial flags are there, like whatever are the states of connection tracking. So those are all handled by OVS. Once the connection has been established, that information is communicated to the OVS engine, from OVS engine to connection tracking library, and then it starts handling it, like when it starts the fast path. So that is a point where things get offloaded. So initial, it all will be done by the software, OVS only.
Then, so once it's offloaded, the sequence numbering and all
Yes.
is managed,
Yes.
right? Like what if again the flows come due to some configuration change, the same flow comes to user space, then the context of sequence number and all that information has to be synchronized, right? Or
No, but the same flow, I mean, like it will be hitting there will be an entry in the NPC, right? In the hardware itself, with the same flow, it hits. So there won't be back to the OVS. It will rather come to the OVS engine, and that's how like if the flow ages out, then yes, we have to remove the context.
I'm saying
if
the
it ages
config
out,
changing.
yes,
Yeah.
if it ages out, then we will kind of at the same time, like whenever the flow ages out, we'll remove the connection. And then like once it again comes next time, it gets the information in the NPC. Once it's there in the hardware, then we start building up the connection again. Like we won't start it from the previous.
Any more questions? All right. Any online questions? All right. All right. So the question is, do we need to install and run a standalone process in addition to OVS?
So yeah, that's the process. I mean, like the OVS offload engine. So it's part of the DAO package. So once we install, so this DAO is a package. Basically, it comes with a Debian flavor right now. And so once we install it, and we have a recipe. So actually, I had one slide on that, but just I had to remove it because of so that was a demo slide basically. So that can actually take us to the DAO page, and where we have a full documentation, like the recipe, how to run the OVS, this additional process, like the additional daemon, like how to run it. So basically it has all the steps. So along with OVS package plus this DAO package, the solution can come up.
Okay, so there was one follow-on question, and it is, does it require any changes to OVS to support this, or is it just?
For now, no. I mean, like because the OVS engine integrates with the PMD basically. So whatever changes, we have it at the PMD level. So there is currently no change at the OVS for getting the path.
All right, cool. I think that answers the question. All right, so let's thank our speaker one more time.